Well, we've made quite a bit of progress this reading module. We have learned to document our work as we go along. We have built one or more regression models. We have evaluated the regression models. We have built one or more classification models and learned how to evaluate classification models. We have even converted a regression result into a classification result so we can compare it against other classifiers. So let's see now what we can do with the features we have in our data set and in our modeling efforts, and see what we can do to help determine which features to keep, which features not to keep. All right, so we're going to turn to our modeling folder, and we're going to focus on this optimization subfolder. And you'll see I've got some options here under feature selection. So let's look at a few of those. We've got forward selection. I'm just going to drag those in here. Backward elimination. And then let's do optimize selection. Now there are three variations on that: brute force, weight guided, and evolutionary. These are versions of this optimize that are basically going to go through a number of possibilities. Brute force being like the name suggests, it's just going to try everything. So you will probably get your best results with brute force, but your feature selection may take a long time. All right, so let's work with forward selection. Forward selection basically is going to start with 0 features and then keep adding a feature at a time based on which one it finds most informative. And then it will stop at whatever number of features you tell it to. So I can say keep 10, keep 6. All right. Or it will stop when it doesn't find any increase in performance. Or you can put some other specifiers without a significant increase, without increase of at least. All right. So let's set this at 9. Okay. So I can say keep my 9 best attributes. All right. My next one here is backward elimination. And here again, you can see basically I'm seeking a certain number of features in my final solution. Backward elimination, as the name implies, is going to start with all your features and then eliminate your least informative feature or your most harmful feature, maybe at the beginning, until it gets to the number of features you specify. All right, and here you can see it stops when there's a decrease in the model's performance or a decrease of more than or that's significant. Okay, so those two are pretty straightforward. Now, all three of these are going to work the same way as far as putting these into your process. So let's take a look. If I click on these, you can see these are set up as sub-processes. So I'll bring my forward selection. Yeah, there it is. Backward elimination, same thing. So I'm going to go ahead and take those out of my process now and focus on optimize. And here you can see I can do forward or backward for optimize. I can choose which direction it is going to work in. So this is a little bit quicker, as you can imagine, than the brute force, weight guided, and evolutionary, which have the options to move in different directions, go back and forth, and even skip around. All right, so optimize selection, I can give it a forward. I'll say forward. Limit the generations without improvement. If I don't get improvement after, say, 2 generations, okay, let's stop that. I can even tell it to limit the number of generations in general. Okay. I'll use a local random seed to tell it where to start. Be sure to use yours if you're doing this for a project in my class. This one actually has a little visual that you can show while it's running, show population plotter. That's kind of a fun thing to see when it's going. And I can even tell it how many generations to go. The default is 10, but I could set it up as many as I want. Well, let's say 25. Give that a try. And I will leave the rest at their defaults. So again, I open this up, there's nothing. So what I'm going to do is basically I'm going to take my modeling efforts and put them right inside this optimized selection. So Control X, Control V, and I'll bring my examples in here, go back up to my process, and connect my data prep for my deep learning algorithm that I'm using here to optimize selection. Now, one thing you'll notice here is I don't have a model coming out of this. So this gives me the ability to use another operator. This one's called remember. All right, so you can see this is under utilities, process control. So I'm going to click remember here, and I'm going to bring the model into there and say, remember this model, and I'll just call it deep model. And there are all kinds of different things you can tell it to remember. I'm asking it to remember a model, so I'll just go to model and remember that model. Okay, so this is basically a way I can store this model in this particular process, even though I don't have necessarily an output port for it from this particular operator. So I go back up into my optimize selection, and I'm going to send my performance, which is now, let's see, performance is going into this first AVE. So I'll connect that to my performance port there. Okay. And that's the only one it gives me. So I'm going back here, and now I can recall that model that I was using earlier. And I think I called it deep model. And bring it into my apply model to population. All right. Now I will take my weights out of the optimized selection, my performance. Let's see, what do I have coming out of there? Performance, yeah, I want that. And then I will see my labeled examples coming out. I think if I just show my examples here, it's just going to be my original examples. All right, so I've got 5 things coming out at the end. Let's see what we can do to optimize our selection. Yeah, we've already filled this in. Let's give it a run and see what we get. I also remembered to use my all right, so let's run this and see what we get. Okay, take a look at my output set. I've got 1, 2, 3, 4, 5, 6 features. Here's my performance vector, 68.5% accurate, 0.765 AUC, F measure of 70.70. I've got attribute weights here. Six of them are significant, 5 of them are not. And here's my deep learning model. So let's see, what I'd like to be able to do is go back up to my main process, and let's take the examples out of my optimized selection and store them in the repository. So let me find my store operator. And I'll put these in my data folder, and I'll just call them optimized bike buyer, or bike buyer optimized. Now I've got a number of outputs connected to my output wall, my results wall here. One of these is the examples, and what this is going to do is be the actual optimized data set with the features we don't need missing from the data set. So let's see if we can capture that. I'm going to use the store operator now and bring those in here. I'll go ahead and pass those through to the wall, but first I want to make sure I have this data available again, and I'll put it in my data folder, and I will call it bike buyers optimize. Duh. All right, bike buyers optimized. Okay, so let's run this process and see what we get. Okay, let's look at this example set. You can see we have 5 features coming out instead of the original 11 that we had. If we look at the attribute weights, we can see only 5 of them have a value. The rest of them are either not helping or possibly even hurting our model. If I look at the performance vector, you can see I've got 56.5% accuracy, an AUC of 0.746, F measure of 67.17%. All right, now let's store those measures so we can take a look at them. And our accuracy, let's see what that was, 56.5%. My AUC is 0.746. And my F1 is 67.17%. All right, now let's keep these here, and we're going to go back here and go back to our original design. I'm just going to cheat and bring the new one right into here. So I've got my bike buyers optimized. I'll drag that in. Okay, so I've got my 5 features. Let's see, head performance vector, accuracy 63.5%. AUC 0.7, so that's down. And F1 of 67.61, a little bit up. So due to the vagaries of sampling and building the validation, I have performance measures that are close but not quite the exact same. My accuracy went up, AUC went down a little bit, F1 up a little bit. So I'm getting basically the same performance with just 5 features. I believe it was 5. Right, 5 features rather than the original 11 features. Okay, so anyway, that's what takes place when we optimize. One thing to keep in mind, if you do use optimize, then you want to make sure that you set your model up to only expect those 5 features coming through. All right. All right, so let's go back and let's do one more. I'm going to turn all these back on. Okay, so we did optimize. I'm going to take my modeling efforts back out. Let's go back into that area and we'll do one more. This one is going to be automatic feature engineering. So this one, and we're going to treat this more or less the exact same way we did feature selection. So I'll take my split validation, bring it in here. All right, now let's see what we have here. So I'm doing my data retrieval, bringing my data prep in, taking my output there. All right, so automated feature engineering. Let's take a look at the parameters. I can set this up to select features, keep everything, or do feature selection and generation. Now look at the number of parameters I have, and it's about to change. I can balance this for accuracy, most accurate or most simple. So 0 would be the simplest, 1 would be most accurate, or I could put a balance in there, so maybe 0.9. Okay. I can show progress dialog. I'll use my local random seed that I like to use, 1, 2, 3, 4, 5, 6. You'll use yours, of course. I could set a time limit on this if I want to make sure it doesn't run any longer than a certain amount of time. Now, I have a pretty small data set, so I should be okay here. Maximum function complexity. So it defaults to 10. The minimum number is 0. I can make this as complex or as simple as I want. Let's try 25. And then this gives me a number of mathematic conversions I can do with my data. I can use plus this plus that, the difference, multiply and divide features against each other, reciprocal values, square roots, the Euler's exponent, log, absolute values, min, max. So you can try everything. And of course, the more you check, the more possibilities it will go through. So it will take a little bit longer. Again, this is a pretty small data set. Okay, so now let's dig in and we'll connect our split validation. And everything's pretty much the exact same as it was before. Let's see. I want my performance, which will be this first gray AVE. All right. And then my model, I've already captured it just like I did before. So I remember it there. Let's see, I'll skip the storing it this time. Skip storing the data set, and we'll just get a feel for what we've got coming out of here. Let's take a look at our feature set, our optimization activities, the log, our model, the labeled data. And we can look at the population coming out of feature engineering to see what's in it. All right. I think that might be, need to update that. All right, let's give it a run. And before we run this, let's use a different algorithm. I just remembered deep learning can be pretty slow for these. So let's go ahead and go to our predictive. Let's do a logistic regression. And we'll just, no, let's don't do that. Let's do just a plain old decision tree. All right. Okay, so now we're going to do feature engineering and see what we do. Let's just double check that decision tree, see what we have. Let's do gain ratio is a good one. Maximum depth, 15. We'll leave the confidence and minimal gain. Yeah, we'll leave all these defaults the same. All right, so let's go back and run this. And you'll see. Oops. I need to reconnect my model. Reconnect my weights. And then, yeah, my weight's coming back through. All right, so now I've got everything connected, I think. Let's go ahead and run this. All right, so we can see it starts building this chart as it goes through every iteration. And it's hoping to zero in on a solution. And when you're doing this automatic feature engineering, it's good to start with a fairly simple algorithm that you know is going to run fairly fast. So you can see how many iterations you should expect in this final. So here we ended up having 50. All right, so I've got a bunch of different feature sets. Marital status, cars, occupation. This one had 4, this one had 4, this one had 3, this one just had cars. Number of cars, this one had a bunch, okay? So now here I can see the apply the model approach. Let's take a look at my decision tree. So my ending tree is pretty basic. The automatic feature generation, okay. I tried 50 different combinations. I went to cars minus children as a measure that looks like it was helpful. Its complexity level is 2 because it includes 2 features and then these other 4. All right. So that would give me the idea, well, then maybe I want to do cars minus children or vice versa. Let me just double check what that was. Yeah, cars minus children. All right. So feature optimization, automatic feature engineering. Decision trees are pretty straightforward, so you might find that your feature engineering gives you more engineered features for your better result for different algorithms. Again, everything we're doing here, whether it's feature selection or optimization or automatic feature engineering, is related to the algorithm we've selected for it. So different algorithms, different results, potentially different feature sets. All right, well, that's giving you enough to chew on, so I will go ahead and end this video, let you get back to finish up your reading, and then think about the project coming up.